Good afternoon, everybody. Got the fall energy here. So I thought that we kind of killed fall break with the makeup classes, but it seems like you guys are pretty lively. A little refreshed, maybe. Just extra lively today. Enjoying the coming. It's not quite cool yet, but cool front that's supposed to come in, I guess, tomorrow or something. How are you guys feeling about the semester? Some yeses, some nos, some eh. Okay, so today I want to pick back up where we left off last time. I do want to ask how you guys are feeling about the exam schedule. I feel like it's not too late to change it. I'll ask that at the end of class as part of a Kahoot sort of feedback thing. But be taking a look. Right now, we're scheduled for it was November 9th, I believe. I'll bring it up to double check. For our next exam, now would be a good time to tell me if you've got 2 other exams that day, right? So go ahead and work towards checking that, and if that may apply to you, so that you can have your informed answer at hand when we get to that. Let me double check that time. So right now our syllabus looks like this. Yeah, November 9th. Okay. I need to update and change some of this stuff. And so I will do that when I update if I need to update the exam date. I'm going to update that soon. I'll also try to have a homework assignment for you posted by Thursday. So that'll be into the kind of chemistry, chemical equilibrium kind of stuff. Yeah.
Do you still have the test that you handed out?
Yes.
I wasn't here. I was over there.
Yeah, so I can anybody that wants their exam that's here and didn't get it, just see me after class. I have those with me on the homework assignment, so that's no problem at all. All right, so with that, my plan today is to mostly go through example problems of various sorts, introduce a concept or two, kind of talk a little bit more about equilibrium stuff, and then as we continue, I want to get a bit more applied in terms of combining the things we're learning just about, okay, here's an equilibrium reaction, we can calculate pH or whatever, but then elaborating into a bigger problem saying, okay, well, now if we have this, a mass balance system that's relying on some chemical that we're adding, which is in equilibrium with something, how much of that is escaping as gas, and solving a more elaborated problem building on the skills we've done. So that's kind of the target here over the next couple lectures. So today it might be a little simple at first, but we'll take a look, work some problems together, and that's sort of my plan for today. Okay, so this one, last time we've solved a similar one. This one says a ferric phosphate solution is prepared by adding 2.4 grams of ferric phosphate to a flask, bringing the final volume to 1 liter. By adding water having a phosphate concentration of 1 milligram per liter. What is the concentration of soluble iron in this solution? Okay, so what they're saying is we have some sort of a flask. We'll just draw a little container here, and we have 2.4 grams of solid stuff, the ferric phosphate, okay? So we have some solid here on the bottom. So ferric phosphate. That's 2.4 grams of it. And then we add 1 liter, and we note that this 1 liter of water that we're adding has some phosphate in it already. So we're adding water that has 1 milligram per liter of phosphate. So phosphate being PO4 3 minus, we have, so let's say 1 milligram per liter of this is in the water at the start of our system. Okay, so then the question is, what is the concentration of soluble iron in this solution? And this is going to be pretty much 2 plus. It will say, might include 3 plus, but we'll keep it simple. And the book here, this is an example from our book, and it's dealing, it may be dealing with a topic that I didn't bother getting into. So forewarning, we might not get the answer I'm expecting, or I would expect to get. If they're dealing with the co-solute stuff, I think they're just saying we have this molecule, so sodium ferric phosphate should be, actually that should be 3 plus, right? Ferric phosphate should be FePO4, and that should be balanced because it's ferric. So that should be what it's asking for. The wording here is a little weird to me. So it says by adding water, having a phosphate concentration of 1 milligram per liter. So I think what we're saying is we already have some phosphate in the system, and then we have our equilibrium reaction. So we have some Ka, and that's going to be equal to, so let's write out our equilibrium reaction first. And so I'm sort of jumping in on this problem with you here. So this would be a solid. We're going to need some equilibrium constant with that, and that's going to be going to Fe3 plus and PO4 3 minus. So that means our equilibrium reaction here is then going to be the Fe3 plus times PO4 3 minus. This is going to be divided by the concentration of a solid, which we're going to take to be unity, right? Because that's the definition of when we have a solid or a liquid, we say that's just 1. Okay, so with this, we already have some phosphate in the water, is what it sounds like. And we're going to have to get a Ka. I need to look that up for you. I should have included that, but it gives us instructions to look it up. So I'm going to grab the, I think it's probably in the slides from last time, so I'm just going to flip to those real quick. For the moment, start thinking about how you can solve that and start setting it up. Okay, the pKa is 21.9. Okay, so give this a shot. I set up most of it for you already, and let's see if we can get an answer here. I think you guys are going to need a little bit more information in the form of a periodic table. So let me look up, I'll give you the molecular weight for phosphate and for iron. So just bear with me a moment, or look it up on by yourself, that's fine too.
like equation? Like can you solve it like?
No, you're gonna need the Pka equation because there's no way to solve for the iron without something dissolving, right? So we have the solid ferric phosphate.
Yeah, that makes sense.
It's dissolving, so we're not. It would be 0 if we're completely ignoring the solubility, but we just said that we needed to measure it, right? So
Yeah, you can't. Okay, that makes sense.
all right, so let me go ahead and walk you through this. Given that we had this ferric phosphate added into there, and this stuff already had in the mix that 1 milligram per liter of phosphate, it's not as straightforward as you might initially expect. So first of all, we need to recognize that we have some solid ferric phosphate. Now, if it's highly soluble, maybe all of that dissolves, and then we no longer have a solid in solution, and then it just all dissolves. But it said this is, it's prepared by 2.4 grams of ferric phosphate, bring that final volume, and that's adding water that already has phosphate in it. Okay, so what is the concentration of soluble iron? That implies that it's not all soluble. Okay, so we have some implication that it's not all dissolved here. So you could be looking for a hint for that, or recognize that we're talking about dissolution reactions and equilibrium reactions, so that's probably the case. But anyway, that should help you if you tip you off to that. It would hopefully say dissolved if we're talking about, not a solubility reaction here. 2.4 grams is dissolved into, rather than phrasing like this. Okay, so we know that we have this Ka, 10 to the negative 21.9, that was given in the book, and we know that's related to the iron and the phosphate. Now, if we take a moment to think about what this would look like if nothing else was in the system, it was just this equilibrium reaction, this would actually turn out to be, okay, we don't have to think about it, we just take these two here, and we know that there's a one-to-one relationship, because each time you dissolve one molecule, you get one of each, right? So then if the system was completely simple, then we'd have equal amounts of the dissolved iron and equal amounts of the phosphate. So then we could do that substitution we talked about last time, saying, oh, well, this is just like 10 to the negative 21.9 equals to x squared, right? So we have x times x, if they're the same thing, and then solve with the square root, right? And then that's our answer. And if we did that, that turns out to be about 10 to the half of 21.9, right? 10 to the 10.9, or whatever that comes out to be, 11, almost 11. So that would be the simple way, right? That would be the direct way if nothing else was in the system. But here we have a problem, because we're told we have some amount of this, and we don't have enough iron to create more solid. If we had enough iron in solution, like a separate source of iron, then maybe we'd be precipitating iron, and that would be, we could maybe get equal here. But the deal is we have extra phosphate, and so what's going to happen is that's going to push the reaction towards the left. It's going to bias the reaction leftwards, so we're going to have less iron than we would have if there was just pure water. Okay, so that's the way this is working, because that reaction, the reaction towards the solids, has a component that depends on how much phosphate's in the water. And so that's a continual driver moving that portion of the equilibrium left. So what do we do then? We need to solve for the phosphate, and then we can really just say that the iron, so Fe3 plus, is going to be equal to that 10 to the minus 21.9 divided by whatever we solve for this phosphate concentration. Now, you may be thinking to yourself, well, this is tricky, because as soon as some stuff dissolves, we've got more phosphate in the solution. That's correct, and certainly a valid consideration. But if you do take a look at the values here, maybe we can go ahead and just put that thought on pause for a moment and say, well, with that 1 milligram per liter, what's the moles per liter we get with that 1 milligram per liter, right? So let's take 1 milligram per liter of phosphate and convert that into moles per liter. So first of all, we take that 1 gram per 1,000 milligrams, and then we can take this and essentially divide it by the molecular weight of phosphate. So we'll do 1 mole per 94.97 grams. So that's the division there. And when we do this, that should give us the molar concentration of phosphate per liter. And that's going to be equal to, did that in Excel here, we've got 1.05 times 10 to the minus fifth. Moles per liter. Okay, so that's kind of the first step. And again, if we come back to that thought a moment ago that as soon as we start dissolving this ferric phosphate, we're adding phosphate to the system. Well, is it relevant is my question. And I mentioned a minute ago that if we have the nothing in solution, pure water, this is driving the dissolution. We said that each of these components would be around half of this, or I guess the square root of this. I'm sorry, not half. So the square root of 10 to the minus 21.9. We can half the exponent, and that's doing the same thing as taking the square root, right? So that's meaning that if it was pure water, the amount we would add would be 10 to the minus something like 10.9 or whatever, 22 divided by 2, right? So it'll be almost 11, 21.95. That's going to be the scale. So if we're adding phosphate at a level of 10 to the minus 11th moles per liter, that would be like, okay, yeah, we did add some here, but that's 0.00000000001, right? It's such a small rounding error that it's not going to affect our answer here or affect the effective amount of phosphate. So we're just going to ignore the amount of phosphate added for that reason. So that means that we can just put this number into this here, do 10 to the minus 21.9 divided by 1.05 times 10 to the minus fifth, and that's going to be our answer for the iron. So that's going to be, let's write it out. Well, I'll just show you in Excel actually. So we'll take our Excel page. Oops. And here we have the molecular weight of each put in. We got that concentration of 1.05 times 10 to the minus fifth. And we solved based on essentially taking that Ka, which 10 to the minus 21.9, and divided it by the phosphate that we found. And our answer was 1.2 times 10 to the minus 17, which is what the book gave us. So great. So 1.20 times 10 to the minus 17 there, moles per liter. So a lot less than we would have had we just had pure water. So that little bit of phosphate that we had in there prevented the dissolution of the phosphate, of the ferric phosphate to an extent. So it turns out the 2.4 grams here did not matter at all. So that's just a red herring, you might call it. So a part of the problem, you know, they added some amount, so they weighed it or whatever, but it didn't have relevance to the problem. Also turns out we didn't need the molecular weight for iron, or the atomic weight rather. Okay, any questions on that? That makes sense?
So, like, if it was pure water and both of them are being dissolved in them without there being any prior phosphate, then you would just take the square root of the Ka?
Yeah, if it was pure water, in that case, you could take the square root of the Ka because there's a 1-to-1 here.
Okay.
If it was not 1-to-1, you'd have to act accordingly, because if it was like 2 and 1, then your equation, well, first of all, you have a square here then, right?
Yeah.
And then you'd say, okay, in addition to that, your concentrations are different. So in this case, since it's 1-to-1, you know those two concentrations are the same if those are the only sources. So you'd have to calculate a relationship. It's like the book, and the example from last time used S as a substitute. It's like you have S times S, so it's S squared. Yeah. And if it was different, then you'd say, okay, well, the iron was 2S and the phosphate was 1S. And so then you'd have 2S squared times 1s or something like that, right? Whatever made sense algebraically.
Okay. That
Yep.
makes sense.
If the ferric phosphate was like aqueous, would that mean you would have to use the 2.4 grams?
Okay, so the question is if the ferric phosphate was in the aqueous phase, then would we need the 2.4 grams? I'll say yes. So if we were to somehow supersaturate the solution and achieve a ferric phosphate or achieve dissolution of the ferric phosphate, 2.4 grams of it, and then we need to calculate the I guess the solubilities, because you're going to have precipitation at that point. What you would need the 2.4 grams to know is whether or not you were above the solubility limit, right? Which would become obvious when if you've worked with some of these problems and you recognize a couple grams, that's going to be a molar equivalent of something 10 to the minus fourth, fifth, third, somewhere around there. And then you're looking at this 10 to the minus 11th, where it would be. You should recognize in your mind that, okay, you're going to have some precipitation. But you could check that. You could check that mathematically, and you would want to use that 2.4 grams to check it. So, yes. That makes sense. Cool. Okay. So, wanted to talk a little bit about some pH and do another just very basic pH. Oops. Accidental puns are the best ones, right? A very simple pH problem here, but just kind of wanted to highlight a few pH regions and what you might expect to find for different materials, foods, stuff like that. So down at pH 0, or 0.3 really, battery acid. If you're talking about like lead hydride batteries. Lemon juice is actually pretty acidic, 2.1. Wine is 3.5. Randomly, just recently watched a short little YouTube video on marinating stuff, and the reason you'd use wine or lemon, lime juice and stuff is because that acidity will actually denature proteins like your stomach does, denaturing proteins and in some sense digesting them. If you've ever had ceviche.
Tenderizes it.
Yeah, so it's tenderizing, it's opening up some proteins, allowing some of the flavorful juices to penetrate just a little bit into the meat or whatever you're cooking. If you look at pure rain, so rainwater that was just exposed to nothing but our atmosphere with no, let's say, zero pollution, just our typical gas, the air we're breathing, let's say we ran it through purification, the pH actually comes out to 5.6. That's very interesting that it does that. That's the carbonate system. Probably take a look at that next time. But essentially, if you remember, we talked about CO2 gas dissolving. That dissolves and adds a little bit of acidity. So that's what causes natural rainwater to be slightly acidic. Distilled water, however, if you've not let it equilibrate with the atmosphere, is going to be pH 7, right? If we've got absolutely pure water with no carbonate in it, that should be pH 7. If you take baking soda and add it to water, you get something that's about 8.5 pH. That's actually similar, related to the carbonate system, but instead of adding it as CO2, which adds some extra, because we do this reaction, right? And that gives us H2CO3, which is an acid. And so you could then get that, which goes to H plus and HCO3 minus. So that's kind of where the acidity comes from. On the other hand, if you're doing baking soda, do another little call out here. What we're talking about there is typically sodium bicarbonate. So Na2CO3, which has a 2 minus, and that's going to CO3 2 minus and 2 sodiums, each with 1 plus. Now that adds a little bit of a basic effect for the same exact reason, in that we can take CO3 2 minus plus H plus, and that goes, what's in equilibrium obviously, but goes back and forth with HCO3 minus. Now, the reason I say that's causing some basic aspect is because it's going to consume some of those hydrogens when it's doing this equilibrium. So it's just a way to shift it a little bit. That's what happens there. You can add then some lemon juice or some vinegar and move it all the way back up to the CO2 gas and get your little lava fountain of vinegar and baking soda because you're off-gassing the CO2. Okay, household ammonia is about pH 12. Household lye, that's sodium hydroxide typically, that's what that's referring to, NaOH, is directly adding OH, which is what we consider base. It's the conjugate of H+. Okay, so that's pretty straightforward stuff there. Just wanted to kind of elaborate a little bit. We have a problem here. And this one probably is quite simple. So find the hydrogen ion concentration and the hydroxide ion concentration in tomato juice having a pH of 4.1. So this would be a good quick double check that you're comfortable with the pH system. Should be able to do that, and it shouldn't take you very long. So go ahead and hammer that out. Make a little space. So as you see, I sort of wrote the answers up there, or the beginnings of them. So for H plus, we really should just be 10 to the minus 4.1. That's the definition of pH, right? So that should be, if we were to solve that in a calculator, 7.94 times 10 to the minus fifth moles per liter. The hydroxide, that's OH minus. You can know that because if we have water, we know the pH, then we should know both the H plus and the OH minus because of the equilibrium, right? The 10 to the minus 14th, if you don't have that memorized, memorize it now or know how to derive it. That's equal to H plus times OH minus divided by the 1. So you can rearrange OH minus is equal to 10 to the minus 14th divided by 10 to the minus 4.1. And even without using a calculator, you could subtract those and say that's 10 to the minus 9.9. Subtract the exponent. And if you do that, that should be 1.26 times 10 to the minus 10th moles per liter. And of course, that's hopefully what the book is going to tell us is the correct answer. Cool. Okay, so if that was not very simple and straightforward, happy to help work you through that. At this point, I'm hoping that is very simple and straightforward, just to double check that you know that. Okay, so here's a little bit more complicated one. So we have chlorine as the active ingredient in most household bleach. It's one of the most commonly used and inexpensive chemical disinfectants for water. The chlorine in the hypochlorous acid form, HOCl, and the chlorine is in the hypochlorous acid form, HOCl, and that's a much better disinfectant than hypochlorite, OCl minus, its conjugate base. If the bleach is used to disinfect water, below what pH should the water be maintained so that at least 95% of the chlorine added is in the hypochlorous acid form? So what pH do we need to keep that as 95% of it to be the desired hypochlorous, HOCl? And by the way, I think the problem is misspeaking here. Your household bleach is often in the OCl minus form. It's usually NaOCl dissolved into water with some additives to keep it stable, and that's a little safer than keeping it as HOCl. Also why you don't want to add acid to your household bleach typically.
Not any mustard gas or something?
If you add ammonia, you'll get chlorine gas, I think Cl2 gas coming off, and you'll get chloramines, which also are irritant and tend to stink. If you add acid, you're going to get mostly this, which may also be able to off-gas. I'll have to take a look at the chemistry, but maybe that too.
Yeah. I read somewhere about
Yeah, and mustard gas, I think, is the common term for chlorine gas. So this is our equilibrium reaction. I'm going to go ahead and say that Ka should be about 10 to the minus 7.54. It's going to vary a little bit by temperature.
How did you get a Ka value?
Been doing this too much. It's just supposed to be given, and I recognize. So the question is, how do I know it? I've just done this problem too much, or this type of problem, and you should be given it or have a lookup table to know it for yourself. right, so as you're thinking about how to solve this, there's probably going to be a few methods you could use in terms of the algebraic formulation of it, but what makes sense to me is to say, okay, since we want 95% HOCl, that's going to be, if you take HOCl divided by the total chlorine in the system, which is just HOCl and OCl minus, then that should be a ratio of 0.95, right, at minimum. So that fraction there, that ratio there, is just a description of what it means to be what percent of the total, or what fraction of the total is HOCl. You could do that for OCl minus as well, which is just putting OCl minus at the top. So the important thing to note there is that the total amount of free chlorine, I say free chlorine, that's kind of just the term for these chlorine species, is equal to the HOCl plus the OCl minus. Okay, and in terms of, in a molar sense, that would be the molar concentrations of them. Does that make sense? Conservation of mass there. So that means that we can, in a way, arbitrarily say, okay, well, there's some total chlorine, and that actually becomes really helpful if, like we were talking a few minutes ago, if we added some mass of chlorine, and in this case it's all dissolving, there's no solid form, it's just all dissolved. So in that case, we might have some solid, some gram amount, some mass that we add, and that dissociates into these two species, but we could still think about the total amount that was added based on whatever form we added it in. Okay, so from here, you need to relate this to our equilibrium reaction in some way in order to achieve our desired result, which is solving for that H plus, right? We need to solve for H plus, excuse me, given that we have this ratio holds true. So let's go ahead and rearrange and say H plus over here on the left. Let's rearrange this, so that would be equal to 10 to the minus 7.54 times HOCl divided by OCl minus. Okay, so that gives us an equation for H plus. That also means we have some, we can see that there's a ratio here, HOCl divided by OCl minus, which might be handy when we're taking a look at this relationship over here. So let's manipulate this equation over here that we have this 0.95 equals all that, and see if we can get it into a form that is compatible with what we have over here. And by the way, as I scanned this and took a look, I glanced at the book solution. I've done similar problems, but I haven't worked this one with students in class before. I noticed they were doing something kind of interesting. I think my approach here will work, but in case it dead ends, I apologize. So let's take this over here. If we divide the top and the bottom by HOCl, that'll actually simplify our system. So we can say, let me take what I'm going to do is I'm going to divide the top and the bottom by HOCl. So we get 1 over 1 plus OCl minus divided by HOCl. All of that is still equal to 0.95 because I just divided the top and the bottom there. And so with that, I think we should be able to, well, you know, what we can do is we can rearrange this guy, and instead of having HOCl and OCl minus, which can substitute into here, what we could do is say, and I'm sorry, I'm going to try to make this a little bit clearer, follow where I'm going. What I'm going to do is I'm going to, instead of solve this for H plus directly, I think it'll work if we instead say solve for OCl minus divided by HOCl, so that we can put that, we can substitute in here and have H plus there, and then solve for the H plus with all the things known. So that's my plan here. A little bit roundabout. I think there's probably a more elegant solution out there, but this should get us there. So if we were to rearrange this, I'm going to start up here and just divide the H plus from both sides and say this is going to be equal to, I'm just not even going to use this part. So I'm just going from there. I mean, that's true and all, but we didn't really need it. So the OCl minus divided by HOCl, that would be 10 to the minus 7.54 divided by H plus. Okay, then we can substitute that into here and say 0.95 equals 1 over 1 plus this 10 to the minus 7.54 divided by H plus. Okay, so then we need to do the algebra to solve for H plus. I don't have space for that, so let me what I'll do is I'll just write it here and then see what the book says. Yes, question.
For where you have the HOCl, like the equation equals 0.95, can you just simplify that to 1 plus HOCl over OCl, and then just plug that in?
Say that again?
So where you're at right now, can you just simplify that fraction as 1 plus HOCl over OCl, and then just subtract the 1 so you get the number for HOCl over OCl, and then just plug that into the equation you cross out?
I'm not very good at hearing the equation spelled out and visualizing it, so I'm so sorry. That might be possible. So if it makes sense algebraically, so you're saying to substitute,
Just simplify that.
Simplify
as
it.
1.
Which part?
Where your
the
dot
top?
is at, just do it as 1 plus, and then a separate fraction of HOCl over OCl. Yeah, OCl. And then you just subtract the 1.
Okay, so if this is, and then you subtract the 1 from both sides.
And I have the number for that, and then just plug it into the equation cross out.
Yeah, and the way you simplified that was to take, yes, yeah, because you can, see, does that work? It works? Yeah, sorry. Okay, so, and that's just because you could take the 1 here, and then you have, yeah, so I think that's the elegant solution then, right? So this would be the very quicker way to do it. Thank you. So either way, if you want to be weird like me, you're welcome to. You should get at the end of the day an answer of 10 to the minus 6.32. So pH of 6.32. And if you were to take a look at that on your pH chart for the speciation, that should look about right. And you probably could have predicted that just based on, we've seen a couple of these, and the problem even says you want it slightly acidic to make sure that you're in the, in the right spot. And I'm sorry, they used 10 to the minus 7.6 here. I had us use 10 to the minus 7.54. As you see, that's pretty close. If you use their value here, then your answer will be slightly different than if you were to solve this with my value here. But you could just substitute, you can just change that. So I did the long and drawn out inefficient algebra way. There's a very simpler one. But you will get to the same answer, just a matter of steps. So that was kind of the point, and you had to recognize that you can establish a fraction like this, right? And there's probably another way to express that, this way, for example, from the get-go. So that was kind of what I wanted to draw your attention to, is the problem was asking for specifically what fraction of the total is in this form. And so that can be expressed in a couple different ways, or can be manipulated in a few ways. All right, any other questions? So you will have more practice, at least in homeworks, on this type of thing. And we'll get to some that are interfacing with gas phase as well, with Henry's law constants. Okay, I wanted to mention real quick, this is stuff that you'll probably have already had to learn and know on Gen Chem, and you probably will need to learn if you're taking any sort of aquatic chemistry or environmental chemistry classes. Right now, I'm just going to gloss over it. You've learned it before, not interested in you mastering it, but this is kind of where we derive the K, right? So we might be thinking to ourselves, how do we find the K in the first place? Well, it's right there. I highlighted it. It's from the Gibbs free energy. So you probably remember that. Gibbs free energy is related to the ideal gas constant, temperature, and the natural log of that constant is the definition of Gibbs free energy. And you can find that empirically. So based on measurements, you may have done that in Gen Chem lab, measuring as you change the temperature, some reaction is doing something. You might not have known it, but that's probably what you were doing. You can also, then compare two different temperatures and your observations and derive this enthalpy, change in enthalpy with a reaction, and that's another way to derive it. This is, again, relating to knowing something about the equilibrium constant from more of a fundamental level. This is kind of where it's coming from, aside from just looking it up in a book, right? Speaking of looking it up in the book, we've been talking about these reactions where we have the Ka equals some concentration times another concentration, maybe divided by something. And I mentioned last time that technically we could use the squiggly lines, squiggly brackets instead, to indicate activity. That would be more accurate. We're going to keep it simple, but I wanted to introduce this again as a topic. When you have chemicals in solution, it's not always the case that they're behaving ideally like we think they should, right? Sometimes maybe you have way too much of the chemical in there, and then there's some steric effects or other things that are causing the chemicals to not really react or interact in a manner that would be predicted based on simple chemical principles. So activity is a way to define that if you have a whole lot of the stuff in solution, or maybe some other factors that could play a role. And then you use this little activity coefficient thing, and it's really just a factor times your concentration. That's what this activity means. Again, I'm not really asking you to know this, just showing you kind of what that was referring to, what that's about. You may have to deal with this for more advanced courses. It does bring us, though, to a concept here of ionic strength, which is a very simple, straightforward concept I want to go ahead and go over with you. Probably seen it before, I don't know, but ionic strength is a measure of the strength of ions in solution. What do you know? Basically, it's kind of answering how salty is it, without, in a more technical manner, and specifically accounting the charge. It's the quantification of the charge present in solution based on the species there. It's actually very important for water treatment, for causing particles to stick together, the coagulation process. That's definitely where you'll hear it if you take my 3110 class. We'll talk about it there as well. And we have a definition for it, and we'll go through a quick practice problem with it. It's 1/2 of the sum of the concentrations, of all the concentrations in a molar concentrations times their charge squared. That's a mouthful, and this is small font, so I'll rewrite it here. And again, basically, if you have a whole lot of salt in water and you want to know, okay, well, what is the effective role of that in terms of stuff that matters about charge, which the activity is one of them. Again, we're not focusing on activity. Don't need you to know that. I will give you the ionic strength formula here on an exam in case we use it. But essentially, it's 1/2 times the sum, the concentrations of all the species there, times the charge of those species squared. So what that would look like in this example here is, so we have an example here, 100 milligrams per liter of magnesium chloride dissolved in water. I'm going to go ahead and write out the equation. So that I would equal 1/2 times the sum. Well, you know what I'll do? I'll just sum it manually here. We'll say times the concentration of Mg2 plus, and that has a 2 plus charge, so we're going to do a 2 plus squared. The fact that we square the charge means it's always going to be positive, right? If we have a negative charge, we square it, it's positive, doesn't change our calculations or interfere. Times Cl concentration times the -1 squared. That's how we would write it up, right? So in this case, we would need to find the concentrations of magnesium and chloride and then put them in there. So that is very straightforward once you understand what the terms mean. And in this example, we could take 100 milligrams per liter and do that solution. I have a slightly more complicated one for you to work, but we're running low on time. So I'm going to skip ahead to that one and not solve this one. So let's find the ionic strength if we have 50 milligrams per liter of MgCl2 and 50 milligrams per liter of NaCl in the same jar, in the same water. So we added 50 milligrams per liter MgCl2 and 50 milligrams per liter of NaCl. And I'll go ahead and get the atomic and molecular weights here for you in a moment. And just remember that it says I equals 1/2 times, and I do have a Kahoot for this answer, so definitely work this out and see what you can get. Is about ready? Ready enough? Okay. We do want to let you go on time, so let's give this a shot. Got spooky music with it too. You like it? Okay. So, all right. Anybody else need a moment? Okay. All right. Here we go. So I got a couple feedback questions after the answer question. So the first one's going to be pick the right answer. It'll just be like a minute late for letting you out of class, sorry. We'll talk about the solution on this one later. So if you don't see your answer, just guess. Okay, so the green there, 2.43 times 10 to the minus third was the right answer. So we'll definitely go back over that next time. Well, there's one concept in particular that could be easy to forget. Okay, I'd also like to know, did you enjoy the advanced oxidation guest lecture from a couple weeks ago?
He was awesome. He did a really good job. And he
Okay.
said it was like one of the first times he'd done that.
Yeah, and actually he's not great at public speaking. It makes him pretty nervous. So
We finished within like 30 minutes.
awesome. Yeah, he told me it might have been on the shorter side. I was like, they won't mind. no one minds that. Okay, awesome. I'll let him know because I think he got feedback from one class, but not you guys. Thank you.
There's a different class?
Yeah, right now I'm teaching 3110 and this one, and so I had him lecture in both. Does that exam date work for you? True for yes, false for no? Have birthday cake problems? Okay. All right, so who's bringing cake? Is that my job? Okay, so if you have a big issue with it, I'm happy that it's not the majority this time that has a big issue. If there is something, please let me know. If it's just two of you, that may be something we can handle. Problems today's solved, too simple, yes or no. My feeling after actually going through today and going through the lecture, I felt like one, maybe the pH for tomato stuff maybe was on the simple side, but otherwise it seemed all right. Okay. All right. Thank you. If you didn't get your exam, feel free to come by and grab it. Otherwise, we'll see you guys on Thursday.
I didn't know exactly.
Okay. And
But you knew my name.
yeah. What,
Rashad.
sorry, they're all.
Claim reads RIBES.
Sure. There you go.
Number KMBR Cameron. Thank you.
Abigail Bolander. Yeah, I can do it.
Last name Champagne.
Okay.
You don't say like champagne? On banners, you know. Oh, so you do say champagne, but not here. Yep, right. Yeah. That's like the authentic way, I guess. I mean, a few champagne things. Thank you. It smells just like that. Hyper. I'm saying.
Should know everybody by now.
Did you curve it?
No, I have not curved it, so I.
Wait, what? So I actually did well? No freaking way.
The average was a 75.
Dude, I yeah, I had math that morning.
Disperse the studying, calculated average on all.
Just make sure I have.
Thanks.
Mhm.
For effort.
There you go.
Thank you.
Brown. First day was talking.
Yeah, I got you. I just grabbing the homeworks too, which are loose. There you go.
Thank you very much.
Yep.
Oh, I just had a question.
Yeah.
Did you get my advice and form medicine?
I think I did. Yeah, and I should have passed it along already. Has your hold been lifted, or is it still? Has your hold been lifted?